Okay, today, our last calculus-based lecture, we are just going to talk about radioactive decay. It's a fairly simple thing, and then we'll do the 252 teacher evaluations. I'm going to do the 152 teacher evaluations in lab today. So this way, the ones in this packet will be 252, the ones in lab today will be 152, and it'll keep it separate. So don't do another one at lab, right? Okay, we're going to talk about radioactive decay. And radioactive decay starts, as we understand things now, not as it was historically, with an understanding of why radioactive decay occurs. So we've talked before that the nucleus is unstable. It's kind of like if I take this weight and I have it up here, it's kind of stable. If I do just a little bit of tip, it doesn't fall over, right? But a little bit more tip and boom, down she goes. That's the way it is with the nucleus. We're in a situation that's kind of stable but not perfectly stable. And one way that we can model this is by treating the nucleus as a spherical energy well. So we've done the particle in the box problem. And the particle in the box problem, we just had one dimension. Well, with the nucleus, we treat it as a sphere, right? Because that's pretty much the shape of a nucleus. And so we have a certain radius where the potential energy is roughly constant. And then it goes up. And so the potential energy, for a simple model, you'd say the potential energy is a well like that. Now, it's not exactly the same, right? But the particle in a box problem is actually a good analogy for what's going on in the nucleus. But notice the particle in the box, we had an infinite barrier. Well, real life doesn't involve infinite barriers, it involves finite barriers. So if the particle had enough energy, if it had enough energy to be up here, it could get out. For a radioactive nucleus, we say, okay, the energy is just a little bit below the energy necessary to get out. So it's bound in there. But quantum mechanics says that it has enough energy to be out here as well as inside. And using the wave treatment, we have a wave function for the particle, and that wave function will extend outside of the nucleus. So that means that there is a probability of the alpha particle moving from inside the nucleus to outside the nucleus, even though it doesn't have enough energy to get out. And what was it we called that process? Tunneling, right. So there's a certain tunneling probability. And based on our probability calculation, taking the wave function mod squared, we can actually go through and do an integral and calculate the tunneling probability. That is the probability that each time that the alpha particle will tunnel through. So that's the first part. We treat this alpha particle as if it can tunnel, and then we say based on its energy, we'll just calculate its speed based on its kinetic energy. And once we know its speed and know the size of the nucleus, we can say, okay, it's going back and forth in the nucleus, and it hits the side approximately x times per second, based on its speed and the size of the nucleus, right? Not a hard calculation. And so putting those two things together, we can calculate a decay probability. We take the probability of decay for each collision, and we multiply that by the number of collisions per unit time, and that tells us the probability of decay per time. And so that's what this lambda, we call it the decay constant, is. It's the probability of decay per unit time. So now I don't have any clicker questions at all, but what was the basic model used here to calculate a decay constant? Okay, the speed and what was the other one? Is it the size of the nucleus? Okay, well, yeah, the speed and size. Yeah, in my brain I put those together already. The speed and size to give me how many times per second it gets to a wall And then what was the second piece we needed? Those are the things that Tori was talking about. But there was a second separate thing. No, that's the thing. Not the mass. The probability of tunneling each time it hits the wall. Now, keep in mind, of course, this is not the historical way it was developed. The historical way it was developed is they saw that things decayed and that they appeared to have a certain decay probability. So this model comes later, but calculations with this model give you the ballpark value for the decay constant. You aren't going to calculate the exact decay constant with this. It's not a solid enough, fixed numbers and whatnot. But it gives you the ballpark, so we believe it's a pretty good model. Well, how do we use that? We use that by saying, okay, if I have a large number of nuclei, like capital N number of nuclei, and lambda, the decay constant, is telling me the probability per second of decay, then the actual rate of the decay will be the number of nuclei I have multiplied by that probability of decay per second. Right? So if I had 100 nuclei, it'd be my decay constant. Each nucleus has this much probability per second of decaying times the number of nuclei. That would be my expected number of nuclei per second that will be decaying. And we call the rate of decay the activity. So A here stands for activity. Now there's a minus sign in here. Can anybody tell me why that minus sign is there? This is a logic question. Okay? It's because it's decay. What happens to N if I have a decay? N is the number of radioactive nuclei. If I have a decay, it decreases by 1. But the activity is measuring how many things came out. So if I have a decay, it's a positive thing that came out, but it's a decrease in N. And so that's why you have that minus sign, because you're changing from counting things remaining to the things that left.
The negative sign tells you that there's how much is left?
Well, if we have a decay, N goes down. But if N goes down and we have decay, then I have a positive thing that came out, right? Whatever the decay product was. And so when I'm counting the decays, that number goes up as the number of radioactive nuclei, N, goes down. So since one goes up as the other goes down, that's why you have the minus sign. Now we take this equation and, well, it's a calculus equation. And guess what today is? It's Physics with Calculus Day. So we take this equation, we can work with it. And I think I looked at it in lab real quick. Minus dn over dt is equal to lambda n. This is a simple first order differential equation, the kind that you can actually do. So what's the first step to solve this simple first order differential equation?
Separate variables.
There we go. This time we remembered. Separate variables. Well, if I'm going to separate variables, it is really kind of vital that I recognize which ones they are. Name the variables for me, Michael.
dt. It should be t and n, right?
Yep, t and n. So I need to separate those, and when I separate them, I need the d's, the dt and the dn, in numerator positions. So there's one step that obviously has to be done. Since dt is in a denominator position, what do I have to do? I have to multiply everything by dt. So then it'll cancel on the left. Actually, let me be not so lazy. Write the dt twice. So it will now cancel on the left side. So now dt is on the right side, dn is on the left. There's one more thing I have to do, and what's that? I have to move the n over, so I'm going to divide by n on both sides. And I'm actually going to divide by minus n. Divide by minus n, so I just move the minus sign across. And so I have a cancel there, and I'm left with dn over n equals minus lambda dt. The left side only has to do with n. The right side only has to do with t. So these are two independent functions. One depends on one variable, one depends on the other. So they're going to have to be independently equal. I just integrate both sides from my starting condition. So I'll put n0 as my starting number, n final is my ending number, time 0 equals 0 by definition is my starting time. Time final is my ending time. Doing that integral, what do I get? Okay, so there I put my limits, just so we can remember, oh yes, we have to explicitly do the limits here. And so putting in the limits, natural log of n final over n initial. Why did I put it that way, friends? I call you friends. We've been working together for almost a year.
Easier to write that way than natural log twice.
Okay? Because if you put it in, you'd have natural log of n final minus natural log of n0. I just combine them. It's simpler to combine them that way, and then you don't have to worry about any unit problems. Natural log always has to have a unitless argument. You know, if I said n was the number of atoms, and atoms is a unit, and I would have log atoms. Log atoms doesn't mean anything. Doing it this way, the atoms cancel. It's fine. Okay, we want to solve this for, well, actually, let's first solve this for time. Since I'm here, let's solve it for time. I want you guys to work super hard and tell me what this is going to give me if I solve it for time.
It's a hard problem, you know? It's definitely not negative ln nf over n sub 0 divided by lambda, because that would be too simple.
She said it's not this,
Definitely.
but I can read sarcasm. I actually speak it fluently. So it's definitely that. Definitely that. There's a simpler way to write this. What's the simpler way to write it? I could have sworn I had this set like that.
Can we raise it to the negative 1 over lambda?
No. The simpler thing is a minus natural log. What's the way to
You flip.
Yeah. Minus natural log of 1 over 2, or a over b, is equal to plus natural log of b over a. If you flip which is divided by which, it changes the sign. So this is the same as natural log of n initial over n final. See, the n's are flipped over the decay constant. Now we're going to use this on the next slide. So that's why I said, let's go ahead and solve for it now. I usually go to the next step, solve for n, and then have to come back. But why not solve for t now? So now let's solve for n. What do I need to do with this to solve for n?
Raise everything but e to the things.
Yeah. E raised to, as long as I do it on both sides, that's perfectly legit. But what is e raised to the natural log of something?
Just do something.
Just the something. It's the argument of the natural log. So the left side just becomes n final over n initial is equal to, and then the right side e to the minus lambda t final. So solve that for n final. So these two equations are really the same equation. You might recall when we were doing electricity, I talked about in the military where my friend had to learn Ohm's three laws. V equals IR, I equals V over R, and R equals V over I. Well, those were all the same equation. It was real obvious to everyone. This isn't quite as obvious to everyone, but it's also the same equation, just rearranged differently. So, in terms of calculus, we're done for today. There's only a few more things. We're going to finish early, then do the evaluations. In fact, this is the last slide. So here's the equation we just found. Of course, I drop the f's here and just have n as a function of time. And so if you plot that, you get a decay as shown in the brown line here. That should look like what you did in lab, right? Now that's on a linear scale. What did you do in lab to make it so it was a straight line? Semi-log scale. What does semi mean?
You log one side, but not the other.
Okay. In this application, it's you log one and not the other. Halfway, as Sally said, is what I was looking for. Sally's feeling really bad now. I didn't mean to give you the right answer. Really, truly. No, it was perfect. Okay. So semi-log, we logged only one of the two. And it was the vertical axis we logged. We plotted the numbers just as they were, and the axis was scaled differently to make it a straight line. Well, with this decay, why does the rate change? Because it's depending. Yours is a mathematical answer. It's a logarithmic, so it looks like a logarithm. But the physical answer is because the rate of decays depended on how many were present. So if I have less present, the rate's going to drop. And if the rate drops, then that shows up here as the slope. The slope's going to get flatter as we have less and less. So just because the rate is dependent on how many are present, we have that logarithmic decay, and that occurs in many, many things in nature. That's why the E is so prevalent in nature, because we have a lot of things that the rate depends on the size. So because you have the rate dependent on the size and you get this specific curve, it turns out that you can calculate the time that it's going to take for statistically half of the nuclei to decay. So going to the calculation we'd done on the previous page, we had time final was equal to natural log of the number we started with divided by the number we end with divided by lambda. So now to find the half-life we define as the time for half to decay, we just say, and I'm changing color so it's clear, to find half-life, you set n final is equal to n initial over 2, and then find t final. Well, we already have it solved, so this is a one-stepper. So I'll put tau 1/2 for the half-life. And of course, we can all read this and say, I wonder what n0 divided by n0 is. Certainly not 1, exactly. 1 divided by 1/2 is also certainly not 2. So this gives us natural log of 2 divided by the decay constant. So now we can see mathematically where everything comes from for these simple radioactive decay problems. That is the last pearl of knowledge that I have to give you in regards to calculus. Any questions about the radioactive decay? Okay, go ahead. Yes, I don't even know how to answer that. So,
They score the insides of the membrane.
yeah, we threw sand in there to make sure we'd grow. One more statement. The final exam is coming up next week from today. And on that final exam, you will have probably, well, it could be one, could be two. It'll be the one or two calculus questions. And those questions would just be chosen from the topics that I highlighted on each of the calculus review sessions, plus this right here. So to review for the calculus questions on the exam, just go through each of the review lectures, if you will, or all of them. I mean, you can watch everything on YouTube, right? And that should give you what you need in terms of the calculus-specific questions.
How many problems are on the final?
It'll be the same.
10?
Alrighty, that brings me to the end of what I'm going to do here.